All right, good morning. Welcome back to the second lecture of 128A. If anyone missed last lecture, I spent half of it talking about practical procedures. I won't do that again. But this is the homepage, and you can find almost everything I talked about, the practical details on that homepage. I don't think I have too many more things to add except the issues with over-enrollment and sections that people can't make it to. I think David told me that 11 to 12, he had a lot of people that were not registered in that. That's not going to work. What you can do is if you find someone in a section and want to switch, that can be done. Then you just go to the undergrad officers in the math department and they can switch your sections. So, but I know that some sections are more popular than others and that in general it will be an issue. But the official rule is that you got to stick to your section. And it's very important in this course because the room is pretty small, right? Now you have next Tuesday, you should figure this out by next Tuesday because the week after that is a quiz and then you should definitely be in your own section. And well, remember also you have a homework due this Tuesday already. So you got to hand that in to the right GSI. But of course, by the Tuesday after that, you need to figure out where to go so you take the right quiz. But hopefully all these things will work out. A bigger concern, I guess, as I mentioned last time, is the fact that about 30 people are on the wait list. I cannot say, you can ask, the administrators in math department if they have any estimates. But I would guess that all of you are not going to be able to be enrolled. And unfortunately, normally I can just say increase the class size. And one of the GSIs take an extra section. We cannot do that in this class because the room is full. So they won't let us do it, so that's unfortunate. Anyway, let's see. I filled out a few of the office hours. I guess Chris is the only one I haven't heard from yet, but maybe he's communicated with you guys about which office hours he has. They tried to, I see Michael had it on Friday. As you saw, I did not have an office hour. You have homework due on Tuesdays, right? So today after class, I have my homework only for you guys. Homework. I have my office hours just for you guys. So, it's great if you plan ahead. You can come and talk to me about that. You can go to many of your GSIs have office hours on Monday or Michael on Friday. I don't know what Chris has. And of course, I started a Piazza page. Hopefully you got the announcement. Sign up there. I thought I could enroll you guys. Maybe I should have done that. I could just dump all the emails. But it's probably better you just sign up because maybe you want to use a different email than the one I have. Just click that link and sign up. I honestly don't know the difference between that and the discussions in B courses. I would hope, actually, but since people like Piazza, I signed up. See what you like the best. And maybe there will be double postings or something. But for now, it's experimental. We try to figure things out. The B courses thing seems pretty OK, I guess. But Piazza I'm used to, so I've seen it before. You choose. You decide. One other thing just related to the switching section thing, one of the GSIs suggested that maybe you could communicate electronically if you wanted to. Like you could just say, hey, I want to switch from this section to this section. Maybe you could do that through Piazza, and people could respond. I don't know how that works, but you could just post things. Or you just go to the section you want to switch to, and after the section, you just stand there and say, hey, does anyone want to switch with me? I have this section or something. And then, as I said, you can do it formally. But these things usually work out in the end. But I'm just saying that we cannot have, like David, 11 to 12, he cannot have 10 extra students that are not enrolled in his section. You won't fit. You won't be able to take the quiz. That's not going to work. Let's see. I don't think I have any other practical details to mention. Any practical questions that showed up in section Tuesday or that you've thought of or that I missed? Any MATLAB problems? Have you bought MATLAB? Have you acquired it somehow? Hopefully the GSIs told you Tuesday how to use them at least in the basement there. And so you can do that. But I think most of you actually want it on your own laptop, or it's kind of convenient. Well, let me know if you have any trouble with it. I'll be hopefully already today have some time left to start showing a little bit of MATLAB. People ask, I saw someone asked already on some discussion somewhere if you need this book. Well, the MATLAB policy is what it is. This class is not about MATLAB, okay? You can look at the syllabus and see that there's not a single lecture that says, now we're going to learn MATLAB, okay? It's a class in numerical analysis. I wish you guys were expert programmers coming in. Then I could focus more on the numerics maybe. But the good news here is that you will learn MATLAB. a little bit of it, and it's a good part of it. The problem is that it's going to be a little stressful the first weeks, okay? But you'll be fine. So the official answer is no, the MATLAB books are not required. You do whatever you want. You got to learn it somehow. And you'll pick it up. If you haven't seen MATLAB, I would strongly recommend that you sit down with these things. Of all the books I recommend, I think I said last time, I actually am thinking that this might be the best link to go for, because that's a class that was taught specifically to teach people MATLAB as preparation for 128A. So the examples will be taken from that, and that I think her lecture notes might actually, and the examples might be the best way to learn. But there are many books. I know people like this book too, if you want to. This is actually the textbook she used for that little one-unit course back then. So try to pick it up, and as I said, maybe already today I'll be able to show some MATLAB if I have time left at the end. But I will always make demonstrations, and somehow you're going to learn it. Just devote some extra time. The programming assignment will be MATLAB-oriented, of course. And the first one is not due until Tuesday, but I'll post it in a week or so, and you can start looking at it. But this gives you some time to learn the basics. The MATLAB code required for that first programming assignment are very minor. You're going to write like 10 to 15-line codes with very basic structures, okay? You need to be able to define functions and do some simple things. So it's not like you need to be master hackers and do crazy things by them. All right. So let's get started then. Let me know if you have any further questions. Quick repeat of just what I did last time. I should mention that this chapter 1 is different from the rest of the course in a way. It sets up preliminaries that you kind of review, but at the same time maybe not. Maybe you haven't seen it before. The second section is about floating point, and we'll talk about it more today. And it's interesting and important, and I'm sure it's new to most of you, but it's not a big part of the course. But it's important that you learn it. And then again, some definitions in 1.3. Things are going to be more normal to this course next week when we start talking about algorithms and numerical methods. This whole part of calculus, just go through it, review it, read the book. They describe it well. It's not like they are reviewing all of calculus. They are just telling you theorems that you probably might not remember because they're going to use them, okay? So limits, the definition of limits and continuity, sequences. This should be completely straightforward for you guys. What is a derivative? Differentiability implies continuity, right? That's something we know. Differentiability is stronger. It's a smooth function. We're usually, if I talk about the future in this class, we're actually not going to like functions with kinks. Computers don't do that. So like continuity but not differentiability is a bad thing for numerical computing. We want things. We're going to use Taylor's theorem, and we're going to take 4 derivatives, and we want super smooth and nice functions. And if you want to simulate something that isn't that, numerics, that's a problem. So usually we want more than differentiability. But more about that later. What do we have here? Rawless, yeah. I think there is an exercise where you have to use this. It's kind of fun. Mean value theorem, extreme value theorem. This, of course, is kind of important, the extreme value theorem. I mentioned I made an example last week that was very simple where I maximized a function, right? There are going to be functions that, and we're going to ask the question, how large can these functions be? Okay, and I'll come to Taylor soon. The remainder theorem. We're gonna look at that remainder and said, here's a function. How large can it be? Okay, that's another word for that is optimization. You want to find an optimum. It could be minimum or maximum. It doesn't really matter, right? So one way to do that is to use the extreme value theorem if you really want to find the maximum. The good news in this class is that sometimes we can just bound things. We don't have to be that careful. In my example, I had like e to the something. I just set it to the worst possible, right? But I know yesterday in office hours, many people asked, how do you actually do these things? And in our bounds, it's not a unique answer. We can usually bound things without being too careful. This theorem, of course, tells you the true maximum about the function. And you should all remember it. If you have a function going from here to there, the maximum and the minimum value will happen either at the endpoints or at the points where you have stationary points where you have 0 derivatives. And this is Math 1A stuff. You should have done it over and over. But if you really, if you ever wonder, how can I figure out the largest possible value of a function? This is really it. Then maybe you can do something easier and get away with it, but this is the fallback position. Integrals, we're going to compute integrals numerically. In order to do that, it's very important to know what an integral is, and actually not in the sense of the primitive function and the fundamental theorem of calculus, because that's the reason we do it numerically is that that's very hard to do. And in Math 1B, we struggle a lot to teach you guys how to compute all the crazy type of integrals like cos to the m times sine to the n, and we have techniques and tricks. And I'm sure when you took those classes, you realized that it's really not that many functions we know how to integrate. In fact, one of the most integrated functions of them all is Gaussians, e to the minus x squared, because it shows up in statistics and everything, and you really want to integrate that function from minus infinity to some number. You know, if you take any statistics, you know that. And you can't, right? E to the minus x squared it's provably that you cannot express a primitive function to that function using elementary functions. So how do you compute the integral? Numerical analysis. You use the techniques we're going to learn here, right? Of course, you could argue that it's a black box. You don't really have to. There are so many functions doing it for you, but they are using these methods. Turns out that going back to the definition of the integral is the way to start when you're going to define a numerical method. And in fact, the Riemann integral is just, if you remember, it starts by putting all these bars, and then they shrink the bars down to 0. We're going to do the same, but we're not going to shrink them to 0 because that would be too expensive in the computer. So this is just a warm-up for that. Some theories about integrals. This is confusing. You have not seen it before, but you should have seen it with g is equal to 1, because it just says that if you have an area under a curve, you can replace it. There's an equivalent area of a rectangle that you can just replace it by, and there's a value c between a and b such that the function value is equal to the height. It's very simple. The g has to be the same sign. The g here is just weighing that, in the sense that I said an example yesterday that imagine that instead of an area, it's a mass, and there's, it could be uniform density, but the g here could be that it's a non-uniform density, and it still works out. So you'll see. The reason it's here is that we're going to use it later. Generalized Role might show up, at least in some exercises. But of course, this one we're going to use already next week all the time, and it sounds completely trivial, but still, it's nice to have a theorem from analysis that tells us something true, namely that if you want to go from a to b with a continuous function between a and b, you have to pass all values between a and b. And one practical benefit we'll use next lecture of that is that if you want to find the root to the equation f of x equal to 0, if you find 2 points, one where it's negative and one where it's positive, you know there's a root in between. Okay? Now, if the interval is wide, that's not a lot of information, but then maybe we can shrink it so you have 2 points that are really close to each other, one negative, one positive. Right? Then the root is pretty well approximated. So that's what we're going to do. It's called the bisection method, and it's the first method we'll talk about for root solving. Taylor, of course, is really the most important part. We'll do it all the time. I know people don't appreciate Taylor that much, but you should really try to get a good feeling for this. It's like one way to see the remainder theorem here. So this is written in one particular form, where we actually take the function f, and we say that it's equal to its nth Taylor polynomial, plus, you could, if you wish, a cutoff term, right? Because in analysis, in calculus, we know we write it as an infinite series, right? E to the x is equal to the sum of 1 plus x squared over 2, etc., right? Now, we don't want to go to infinity. That's impractical, so we cut it off. Now, you want to know how bad is it that we cut it off. And the answer is Rn of x. It's a remainder term. And I think the part you like the least is that there's a psi that nobody knows what it is. And what's the use of an expression if there's a number that we don't know what it is? That's a very valid question. And the answer is that, yeah, indeed, it's not. There are some cases when it really doesn't tell you much. But suppose at least you know that this psi here is between the center point of the Taylor expansion x0 and the evaluation point x, which means that in the book they have a great example where there's cos of x. Okay? It doesn't matter that you don't know cos of psi, because cos is always between -1 and 1. So that's some information. In my example, it was e to the x, e to the psi, sorry. I don't know psi, but at least it has to be between 0 and 1 in my example, so e to the 1 was the worst possible case. That's what this is used for. But we'll do a lot of Taylor, so you better get used to it. You see, you need a lot of differentiability. Remember this. This is the thing I mentioned before, that we don't just want continuity. When we're going to do Taylor or degree 4, we're going to need a lot of continuity, differentiability on these functions. Anyway, so calculus review. If you feel really uncertain of this, go back and read out. If you don't this is not typical of the course. It's material we're going to use to develop the methods. But mostly we're going to not, it's not a continuation of calculus so much this class. It's going to be quite different later. The next section that I started on last time was this floating point. And it's also usually just one specialized section. We want to teach you guys what's going on inside the computer and what does it mean to make errors in computations, cut things off. Yes?
For most questions in this class, can we just assume that the function given is continuous and differentiable?
Not really. I mean, there are exercises. Maybe then I don't remember exactly what the exercise is, but I could possibly say, oh, suppose the function is just continuous. What happens, right? And the answer would be, well, then Taylor doesn't apply, and things go bad, right? So it will usually be specified. But you're right. We'll come to some sections later, especially the differential equations, and everything we do is going to be Taylor. So it will almost be understood that it's really differentiable then, yeah. But normally we try to be pretty rigorous, saying what it is, right? So that's a good question. But I'm just saying we will in practice be dealing with very smooth functions. All right, so how do we store numbers in a computer? This is how they're stored, OK? And there are various standards, but this standard was designed by a professor emeritus here at Berkeley, and he's around campus if you want to see him at some point and talk to him. His name is William Kahan. He designed, back in the 70s and 80s, the IEEE floating point standard. And it's just an amazing standard that is not just widely adopted. You can't find a computer that is not doing it, OK? And it's so good that you don't even know about it. I mentioned last time, you take Excel, you just type something, and it just works, right? It didn't used to be that way. It used to be that there were different standards. People were arguing about the right way to do this. And I think I'm pretty impressed by what was decided here. Now, of course, there are some decisions in this format. Let me tell you the basic. Floating point, what does it mean? Point is the decimal point, OK? So you can, I told you last time how to represent integers, right? You write a bunch of digits, and they are weighted according to the base, right? So in decimal system, it's 10 to the 0, 10 to the 1, etc. In the binary, it would be 2 to the 0, 2 to the 1. By the way, I made a mistake on the example I made here. It was pointed out after my previous lecture. I put the 1 at the wrong place. But you know your binary integers, OK? So that's easy. Now, how do we do a floating point number? If you have a decimal point, you could just do, 10 to the minus 1, 10 to the minus 2. That's what it means when you write things in a decimal form. That would be a fixed point. The point is somewhere, OK? What is floating point? It means that you multiply it by 10 to the exponent. Or in the computer, 2 to an exponent, OK? Because it means that that point could actually be moved 10 steps to the left by just multiplying by the base to the power of 10. Floating point. The point is moving around. It's kind of the same thing as the scientific notation or the engineering notation, that we don't just write the number and the decimal point. We also do times 10 to the exponent. That's how simple it is. Now, doing that in the computer, you have 3 things you must represent. One is the actual number. The other is the exponent. And there are some issues, but basically the actual number, the exponent, and you need to say if it's plus or minus, right? Which you could argue is in the number, but we'll keep that separate, right? So these are the things you're going to have to put. And how much data can you use? Well, that's in decimal system. You could write 16 digits and say I'm done. You could write 30. It's a decision. The more you write, the more it costs, the more storage in the computer. So what turned out to be the winning design was to devote 64 bits to these numbers. And there are some people who want more precision. There are some people who want less. But this is really dominating all computations. Then the question is, how much should you put on each? You need a sign bit. The sign is 1 bit. Either it's plus or minus, right? So let's just take one of these guys, these bits, and say if it's 0, it's plus. If it's 1, it's minus, OK? So that, of course, means that we get this term multiplying the whole thing. So that's easy. Then we got to be able to represent the exponents. And the question is, how much do you need? And that's a big decision. But they decided that after 10 to the power of 308, it's OK to give up. And there are many reasons for that. One is that the number of atoms in the universe is much less. I mean, it's like 10 to the 80 or something, right? It's just you could argue that, of course, in math, you can make anything blow up. But it doesn't make sense to model things on the order of 10 to the 100. So at some point, it's just going to be so big that you can't represent those exponents. And then the computer is actually going to do something very smart and give you a number called infinity, which is not a number, but it will actually give that to you. Of course, you can go minus by putting the sign bit to 1. You can go minus the same thing, right? But anyway, that's a decision they have to make. At the same time, how close can you get to 0? Well, that's negative exponents, right? And it kind of makes sense to make it symmetric. So basically, you can go to 10 to the minus 308. Or where does 308 come from? Well, it comes from devoting 11 bits to this binary exponent, OK? So basically, 2 to the 11. So that's just an integer between 0 and 2 to the 11, which is about 2048. So why don't we just take that number and subtract about half of that, and we'll be able to go from about minus 2 to the 10, I suppose, and plus 2 to the 10. That's how they were thinking. So far, we haven't treated the number, but we can put a sign there, and we can multiply by 2 to the minus 1024, all the way up to 2 to the plus 1024. Okay? Now comes the number. And it should be something like, so you might be a little curious why it says 1 plus here. That's just a way to normalize it. Because if you think about the scientific notation, it's not unique. I can say 1 times 10 to the 3. But I can also say 0.1 times 10 to the 4. And a lot of other options, right? So sometimes you have to decide on normalization. That normalization is that it's always 1 point something. Okay? Makes sense. So this whole f is really this. What's the weight of this guy here? It's going to be 2 to the minus 1. Okay? It's the first digit after the decimal point. And the actual number represented is 1 plus that. And then, of course, this is 2 to the minus 2, all the way down to, well, the remaining bits are in this mantissa here, which is 52. So this will be 2 to the minus 52. Right? These are the numbers we're talking about. So I showed some examples last time. I did it in MATLAB, which was convenient because I have my little function, num to bin, right? Where I could, for example, do the number 1. And you can see, well, maybe this is not the best example. Here's an easier one. And by the way, in MATLAB, I'm going to do format compact, just so it doesn't make so much space. 2 is an easy one. Sign bit 0, meaning plus. The f, the mantissa here, is equal to all zeros. OK, sounds good. Only difficulty is the c, which has a 1 in the 11th position. That's 2 to the 11. Sorry, that's 2 to the 10. Because the first one is 1. It's 2 to the 0, right? So 2 to the 10 is equal to 1024. Then you subtract 1023, and you get 1. So the number we're representing is plus 2 to the 1 times 1. That's 2. Okay? What if I want to do 4? Will it touch f or c? Turns out it has to mess with c, right? Because f, the best it can do with f is going to be something like, the biggest f you can do is 0.111111, right? You can never go to the next exponent. Very similar to, you got to flip the sign of the exponent to do that. So all you do is to just add 1 to c, the exponent integer, right? What if I do 3, though? Well, then you have to go back to where you were and put something in f. And in this case, it figured out that 3 is actually equal to 2 times 1.5. So by putting a 1 here, I told you this is worth 2 to the minus 1, right? So it's worth 1/2. So 1 plus that is 1.5 times the 2. That's how it works. OK? The next one would be a 0.4 times 2. So what about 3.5? Well, then it's putting one guy there, right? This is it. So in principle, I could give you any of these expressions, and you can go back and forth between these. Actually, going in and looking at that and going to the number is easy. You just plug in. Okay? Figuring out what the binary representation is can be a little trickier. Just for fun here, what are these smallest numbers? I mentioned there is a number called eps, which is the smallest possible thing you can add to 1 and still be represented. Okay? And that's 2 to the minus 52. If you add half of that, the computer wished it could help you, but it just doesn't know how to represent it, right? So it's really equal to 1. So this is something that you need to know. It's a number that is, in your mind, not 1, but it is really equal to 1 in the computer. Another way to ask the computer that is to say, is 1 equal to 1 plus eps half? Yes. Okay? So this was a logical expression in MATLAB. We'll come more to it later. But by 2 equal signs, I asked, is this equal, right? What do you think this is going to give me? 0, because they are not equal, right? And that's actually the definition of eps, the smallest thing you can add to 1. But here comes then the big question. What is the smallest thing I can add to 2? That will be different from 2. 2. Yes, good. 2 times eps, exactly, right? So if I do 2, remember 2 was the one we started with. If I just add eps, that one disappears, cannot be represented. It has to be 2 times eps. And it's pretty, and then it puts a 1 there. And the reason is that this entire thing is now multiplied by 2, because we bumped up the exponent to 2, right? Which means that this smallest little 2 to the minus 52 is going to be multiplied by 2. So in a way, you could say that you have a precision of 2 to the minus 52 in a relative sense. If you have a number that is 10 to the, suppose you want to deal with the mass of Earth or something, what is that? 10 to the, I don't know, 26 or something, right? You're not going to get a precision of 2 to the minus 52. You're going to get a relative. So you're going to make an error that is something like 10 to the 10. But that's relatively accurate. And we'll define those terms more soon. I'd like to mention just a few special cases. It's not really in the book, I think, but since people asked, it's kind of fun to point it out. Some special cases about these numbers. I mentioned that if you go above the 10 to the 308, it's going to give you something called inf. So they just decided that let's define a symbol called infinity, where they set all the c's to 1 and all the f's to 0. Okay? If this happens, the number is not according to the formula there, but it's something that we call infinity. And it's a cool symbol that you can actually use for things, and I'll show you how to do that. Another issue you might have mentioned, and someone observed last lecture, is that you can't really represent 0. Do you see that? Because f can be 0, but then I'm adding 1. And then I'm multiplying by some 2 to the something, right? There's no way in that expression to do 0. Okay? We need zeros. Zeros are very common and important, right? So let's just make a special case. So that special case is to set c equals to 0 and f equals to all 0. So, of course, if you plug that in there, it would mean something that is not 0. But it is 0 because it's a special case. That's how they did it. A cool thing is these signs. The sign bit we keep. So there are plus zeros and negative zeros. We all know they're the same, but there are some differences related to the infinity. Let me mention one more symbol. NaN. And you will see this when you play around with MATLAB or any computational language. It's considered the death of an algorithm. When you start getting non, things went bad. It means you did something. Infinity is kind of bad, but it might make sense. Non will never make sense. It's what the computer will give you when you do something completely wrong, for example, 0 over 0. 0 divided by 0, you know, is really not defined, okay? So therefore, it gives you a non, and it's represented by also all ones, like here, but f has at least one non-zero. Okay? So these are some special cases. Let me show you how you can count with this. Let's just look to see that I didn't trick you. 0. If you set all the bits to 0, that represents a 0. There's a symbol called inf that sets all these to 1 and all these to 0. But you can actually keep the sign bit and make that minus infinity, which is kind of cool. Now let me tell you why infinity is cool, that you can calculate it with it. Suppose that you do 1 over 0. It's really not defined either. But it's figured out that you can actually get away with it by defining a symbol. Infinity is not a number. It's a symbol we use in mathematics to denote, for example, a limit of a sequence that can be as large as you wish, right? But if we define that to be infinity, it has the benefit that if you later do 1 over it, you can make it 0. And this is the reason we want negative zeros, because it's a big difference between plus and minus infinity. And it looks like a 0. That's because MATLAB doesn't write the negative sign, okay? In fact, if you do num to bin of this, num to bin of that, well, it will actually make it a 0. So 0 is an issue, because plus 0 is really equal to minus 0. And sometimes MATLAB just decides to make the 0. So I'm not sure exactly how to produce a negative 0 here. But it's in the system somehow by just putting the sign bit to 1 in this representation. All right, so inf is cool. You can do 1 over inf is equal to 0. What about inf minus inf? What is that? Inf is a suggestion. Not a number is a suggestion. Do people think it's 0? Well, I mean, I haven't told you what inf really is. It's a hack they did to represent limit. But you should think of it in terms of a limit. So the question is, you have one sequence that has a limit of infinity, right? And you have another sequence that has a limit of infinity. Now you subtract. So suppose the first one is the sequence n, right? As n goes to infinity, right? And then you subtract another sequence that goes to infinity. Let's say the same sequence. Well, then it would have limits 0, then it will be equal to 0, right? What if you do n squared and subtract n? Well, n squared goes faster, so n squared minus n goes to infinity, right? So we have two different examples where they give the different answers. What if you do n minus n squared? Then it's minus infinity. You could produce anything. It doesn't make sense. So the computer freaks out and gives you not a number. Okay? This is how you can calculate with that. Yeah?
So how does the computer actually write that? Does it not do the same?
This one here, you mean?
Yeah.
How it represents non? Let's see. As I said, all these guys have to be 1, and it's a special case. But in order to not make it infinity, they put at least 1 somewhere, which they did. So
How will the computer arrive at that? It must be going to algorithm.
oh, yeah. So this is inside the computer. This is actually in hardware of the processor, how to divide two numbers. And infinity, I would assume, are a bunch of special cases. So when you have infinity minus infinity, these things happen. None can show up. I mentioned 0 over 0, right? It's a special case as well. And it's, so when you start running things, when things go bad, usually you get nons. I mean, infinity non. It's good to know about these things, but I don't want to overemphasize it. But now, since they will show up when you play with MATLAB, it's good that you know what they are. Exactly how they are represented is not that important. It means actually you can figure out what is the largest number you can represent. It means that you cannot use this exponent, right? So you're not allowed. So actually, the largest number you can represent would have to put a 0 there and give you number 1 exponent there. It's OK, but that's what gives the 10 to the 308. Let's see. I mentioned that the gaps change as you go. It's all about relative accuracy. It's pretty clear that when I represent a number, let's say that you're working with electron volts in SI units, and things are of the order of this, right? So there's a number. It's clear now that the accuracy of this is going to be 16 digits, right? So if let's say I divide this by 3, and I want to do this format long to see all the digits, what's the accuracy of this number? Well, the number is about 3 times 10 to the minus 20, right? But I have 16 digits. So actually, the last digit there is worth about 10 to the minus 36. I have 16 digits of relative accuracy, and that's what it's. Because of the floating points, it's all relative. So that's good. But if you're talking about the mass of Earth, whatever that is, let's say 10 to the 26, your last digit, the 4 there that it rounded weirdly, is your uncertainty, right? That's actually going to be a huge number, something like 10 to the 10 kilograms. That's the price you pay for. If you want the mass of Earth and talk about it with an error of less than 1 kilogram, you need more digits. Okay, 26 digits or 16 digits are not enough. You need 26 digits, right? So these are the limitations of the system. Anyway, moving on this. They kind of say, OK, fine, this is the computer, this is base 2. Now we want to talk about what happens when things are not quite exact. And then they flip, and I think it's a good pedagogical way to do, they go back to decimal, OK? So don't think that the computer is still binary, but you should have a feeling now that it doesn't really matter if we're binary or decimal. It's just a different base. So let's go back to decimal and talk about rounding and what happens when you round things, OK? So decimal, now I define a new type of number here. Let's call it a k-digit decimal machine number, OK? So it has the floating point form, because I'm multiplying by a base to the power of an exponent, OK? It's normalized, actually different than the other numbers. Can you see that? The other numbers insisted on all being 1 point something. You cannot do that in decimal, because it could be 1, 2, 3, 4, all the way to 9. So it's a little iffy. They could have decided to define these numbers without the 1, but they could have done it in various ways. They could have insisted that the first digit here is, for example, 1. There are various ways to do it. But this makes sense for binary because there are only 2 options, 0 or 1. For decimal, 0 there, you can't say that it's 1 because it could be all the way up to 10. A better way is to say that this is always 0, and then here are the digits that come after it, right? And you can insist that this number, in this case, is not equal to 0. So that's a normalization. This addresses the issue I mentioned that there are many ways to write the same number. All right, so that's good. let's talk about chopping and rounding. What do you do if you want to represent a number that happens to be exactly this number that can be represented here? Okay, so you can chop it. Chopping means, as the name almost suggests, is that you just skip the last one. So you have a number, 0.d1, d2, and there's a dk, and then in principle, of course, the number could have an infinite length here of other digits, right? Your computer or your system cannot represent it. What do you do with these guys? And there are basically two options. One is set them to 0, and one is do something slightly smarter and round. Okay? And rounding can actually be seen as adding a half of the next digits and chopping. You know how to round and truncate, so that's all good. What's an example here? Well, rounding, and let me get this out of my way. Blackboard. And put back some light. So rounding to 5 digits. Rounding to 5 digits of accuracy. What is the symbol we use for rounding is FL, as in float. So pi is a number. We know what pi is, but I don't want pi. I want a floating point representation of pi. And it depends a little bit on what you're doing. So we all know it's 3.1415. So let me write it first as float. 141535. 1415. I'm messing this up. 9, 2, good. Okay. So now I don't need any more. So we're going to keep up to here, right? And then the question is, what do you do with the 9? And if you want to round it, it's of course going to be that you just chop it and put that 5, but then I insisted on writing it in the normalized form, so it's going to be this, right? And then I have to do times 10 to the 1 to fix that up. So there's that number. While if you do truncation or well, the chopping, it's going to be 0.3141. Well, I did it wrong. Sorry. This was rounding and this was truncation. So you know, it's really what you know it is, but it's clearly a difference. Does it seem to be a fundamental difference? I mean, you would probably say the second one is just so bad. Why would anyone do that? It's just wrong, right? Well, it turns out it's just twice the error. So in the grand scheme of things, you might, if the computer is 10 times faster doing the second one, they could do it. I think most computers today do the rounding. But in the old days, they were like saying, look, it's not a big deal. It's just a factor of 2 of accuracy, and that you're better at. But these are the two different modes you have. So what does it mean? You're making an error. And that seems all good. It seems like you decided on 5 digits. You probably know that's enough, and you're not too worried about this. So we're going to look at some examples where it actually can become quite significant. Just some notation first. What is an error? We will say the word error all the time in this class. It's pretty obvious what it is. You're trying to approximate something. Let's call it P. And you have an approximation. Let's call it P star. We might want to take the absolute value, although sometimes it makes sense to put a sign on the error. But usually, you just want the magnitude, right? So let's define the absolute error as the absolute of the P minus P star, OK? My example with the electron volts or the masses of Earth show that this might not be what you want. Sometimes you want to know how some sort of relative error. In fact, when I say 5 digits, that's already implied that it's some sort of relative definition, right? So what usually makes more sense is to divide by some reference number. And the only reference you have is the true value P itself. Okay? So this is the definition of the relative error. Clearly, relative error does not make sense for 0, which is a problem. So usually, you need to know the notion of both these errors. And depending on the context, you define what you want. What about significant digits? It's something. It's a word that we used. I'm sure you used it a lot. I'm not sure you ever defined it. I'm sure all throughout physics classes, people have told you round it to 3 significant digits. Okay? Now, you kind of know what to do, but do you know exactly what to do? Have you ever defined it exactly? I mean, did I round to 5 significant digits here? Well, it turns out I did, but the question is, what if it was a little bit close? I mean, where's the actual threshold when you would say, no, it's just 4? And that is defined here, very clearly, that the relative error is less than basically half of the last value. So 5 times 10 to the minus t means that you have t significant digits. Let me show you an example. If you do, I'm going to do boring numbers. You set p equals to 1, and your p star equals 1 plus, let's say, 10 to the minus 3. All right? So this is easy because we're dividing by 1. So the absolute error, by definition, is equal to p minus p star, which is 10 to the minus 3, right? So this is the error. I mean, this is the difference between what you want and what you got. Relative error is, of course, equal to the normalized version of this, which happens to be the same because p, the true answer is 1. Okay? How many significant digits do I have here? It's wrong, but it's correct to a certain number of significant digits. Well, you have the definition there. You look at the relative error, 10 to the minus 3, and you basically ask yourself, what is the largest value of t such that it's still less than 5 to the minus, 5 times 10 to the minus t. So t equals 2. Well, that's true, but we can do better, right? T equals to 3. 5 times 10 to the minus 3. That's also good, because we're less than that. Do you have 4 significant digits? No, because this number is not less than 5 times 10 to the minus 4. So we have 3 significant digits. And I guess this example was so simple, so it agrees pretty well. But you can imagine as p changes, the relative error changes, and it's important to have a clear definition. This is what we mean by significant digits. And it roughly matches with your intuition. If you write it out, how many digits are correct, right? But depending on what p is, it could be different things. I mentioned the float. I'm going to introduce some arithmetic, namely that you want to add, subtract, multiply, and divide using floating point numbers, okay? And I'm going to put a circle around those just to indicate that they're going to be wrong, but hopefully accurate enough, okay? So it's kind of a funny notion. I've told you that FL means floating point. You can call it round. You can say, the operation I did here, I denote by the function FL. Take a number, maybe a real number, and put it into this system. And it could be rounding, it could be truncation, doesn't really matter. Let's call it round, okay? But now you're going to do stuff with these numbers, and that's denoted by this approximate or machine addition, subtraction, multiplication, division, okay? So what you have to know here is that inside the computer, you're going to give it 2 numbers. Let's say you give it this number and another number of this form, and you ask the computer to add it, okay? And I guess adding is usually one of the easier ones. But think about division, for example. I mean, you can divide 2 very simple numbers, like 1 and 3. And even if 1 and 3 were exactly represented and very simple to represent, you're going to have to chop the answer, right? So these operations cannot be done perfectly. You're going to make an error when you do operations. That's basically what's going on. And the way these are defined is to say that if you want to take 2 real numbers and add them in the computer, well, the best the computer can do is to round each of the numbers, add them in an exact type of sense, and then round the answer. And think about it, how could a computer ever do anything better? Because you can't even tell them the numbers without rounding them first. Then it can add them perfectly, maybe, that's an assumption, but most computers do that, and then it rounds the result to give it back to you. So it's a lot of roundings here, and that creates a lot of errors. So what can happen there? One of the biggest problems here that usually shows a lot of lack of accuracy is when you subtract almost equal numbers. Let me do a little example here, and then that will explain that more clearly. So suppose we have the following 2 numbers. So you have 0. What did I do? 1, 2, 3, 4, 5, 6, 4. 1.4546. Okay? You're working on a computer that has 6 digits of accuracies. And so 6 digits. And let's say we round, because you like rounding so much. 1, 2, 3, 4, 5. And I'm going to have to round, so I'm going to turn that into a 6. OK? So I'm going to round here, and I'm going to turn this into 5. OK? And going back to what we said before, to you it feels like 6 digits is quite a bit, and it's not a big deal, this rounding. In fact, it's a very small error you made relative to this number, right? In fact, it's about 10 to the minus 6, right? That's the error you made. And actually, relative is going to be the next position. But what can you do with these numbers to make that error matter more? If I add them and the signs are positive like they are here, it will still be a very small change, right? Because it's still relative to a large number, namely the sum of these. The thing that can go bad here, and there are a few other examples, but one of the typical cases are when you subtract almost equal numbers. So let's see what happens. So if you want to subtract these, let's say you subtract these. In the computer, you're going to get 0.000001, right? Or 10 to the minus 6. Well, is that bad? Are you still happy about your accuracy here? No, because the true difference equals that minus that, which is, sorry, this minus that, which is 1.8 times 10 to the minus 6. OK? Now, you can take two approaches here. You can say, you computed a number that was 10 to the minus 6, and this is the true answer, 1.8 times 10 to the minus 6. Did you do a good job? I mean, it depends on whether you're relative or not, right? Suppose that you're a physicist and you're playing around with electron volts, and you know, your measurement equipment only had 3 significant digits anyway. So what happens after this is just noise. It doesn't matter. Well, then by all standards, this doesn't matter either, right? Then you live in an absolute world where this is small according to you. Now, usually, someone will ask you, how accurate is this number? OK? And the answer is it's extremely inaccurate, because it's 80%, or it's far away from this number, right? So you have a small absolute error here, namely 0.8 times 10 to the minus 6. But the relative error has to be compared with the true answer, which is huge. So the absolute error is really just 0.8, or 8 times 10 to the minus 7, I guess. But the relative error is, well, it's the absolute error divided by the true value, minus 6, right? Which is something like 0.44. OK? That's kind of bad. But you should know that it depends a little bit on where you come from and what you're interested in. How many significant digits do I have? Just another exercise of that little formula. The largest number t, such that this number is less than 5 times 10 to the minus t. T1 works, right? You're lucky. Had this been just a little bit bigger, you would have 0 significant digits, which sounds horrible. And that's an example of what I said before, that significant digits is maybe not so, you know, maybe not so intuitive. If you look at these numbers, 1.8 is the true answer, and I gave you 1. How many significant digits do you have? Well, it turns out, according to our definition, it is 1 significant digit. But if you bring this number above, let's say this was 2.1 instead, you would have 0 significant digits. That's how the definition works. This is 1 significant digit. So, you know, pretty bad result, given that you were computing with 6 significant digits. But subtraction of almost equal. Here's a more formal way to see that. If you have a number that goes up to dp, and then it has a bunch of other digits, right? So in our case, the dp was the 5 here. They agreed up to this point. Then you get stuff that is different, the alphas and the betas. When you subtract these, of course, all these guys here will subtract out, the d1 all the way to dp, and you will get some new numbers, but you're losing precision exactly those p digits. So that's the phenomenon I just explained. Yeah.
Why is it one significant digit?
Well, according to the formula, you mean, or according to intuition? According to the formula, it's really just that, right? 5 times 10 to the minus 1 is 0.5. So this is less than 0.5, and therefore we say. So according to that definition, it's clear. Intuitively, as I said, I don't think you guys, you've used the word significant digits for many years, I'm sure, but I don't think you ever really ask yourself, is this 1 or 0? It's really obviously accurate, right? That someone wants this number and you give it that number, and you're almost half off, right? But what does it mean? According to our definition, since you're not quite half off, it's 1 significant digit. Had you been more than half off, it would be 0 significant digit. So that's the story. But I'm not saying it's completely intuitive, that significant digit thing. Just use the definition when in doubt. That's the easy thing about math. So this is about what I wanted to show you guys on this thing. There are some exercises where you do these things, and I hope you can enjoy those. I'd like to go on with this section 1.3, which are slightly different things. It's a bunch of definitions. Error, growth, and stability. So this is about, so clearly, every time you touch a number in the computer, you're making an error, okay? Is it bad or not? I showed you a case where you could do one single subtraction, and it was really bad. Hopefully, we're going to avoid that most of the time. Still, suppose you add them. I said that, relatively speaking, you would make a small error. But suppose you do it 1 million times. Remember, computers are there to do 1 billion calculations per second for you, right? And people are doing this all the time, especially in numerical analysis. This topic is the reason for, or half of the reason for all these supercomputers that you read about in the news. People are computing huge things. And you might know that the fastest supercomputers are doing petaflops. They do 10 to the 15 operations per second. Okay? In fact, we have computers up on the hill doing that type of performance. So here's a question. Suppose you add two numbers, like in MATLAB here, I said that if you just add, any two numbers, let's make them a little interesting like that. You get an answer, and it's going to have an error that is about 10 to the minus 16, understandably, because the true answer cannot be represented, so it's going to chop it off. Okay? Sounds like that's not too bad. You're happy with this answer, you did it in Excel or whatever, and it's just good enough because it's 16 digits. What if I now do 10 to the 15 operations on this, and I introduce an error of 10 to the minus 16 every time? Well, suppose they all add up, those errors. That would be complete garbage coming out, almost.
Why the error is 16?
Oh, 52, you mean?
Yeah.
Because that was binary. I jumped back and forth between binary. You had 52 binary digits, which turns out to be 16 decimal digits. I guess 2 to the minus 52 is about 10 to the minus 16, yeah. But you see, adding up a lot of errors can be bad. Now, my example, do you think I was pessimistic or optimistic when I said that they all add up? It's a little pessimistic in one way. There's like a factor of 2 they could cancel out, but there are some theories showing that it's kind of what's happening. The truth is that we got to create algorithms. There's something much worse that can happen. So my example was what's called linear growth of error. Okay? You have a number n, and that's, in my example, 10 to the 15. I'm going to do a lot of additions, right? And there's a constant. I don't care about that. But then I make an error, and this is 10 to the minus 16. And my argument was that if you're doing an error of 10 to the minus 16, 10 to the 15 times, you get a pretty significant error if you add them up. Now, believe it or not, this is kind of the good case, because it's at least just linear growth of error. Now, I can show you examples where you introduce an error of 10 to the minus 16, and you do 10 steps of a little simple expression, and it blows up and gives you complete garbage. Those are the type of things we want to avoid. Let me give you 2 examples of these. They are a little made up, but they still show the effect. Oops. So the linear growth, what's an example of that? Let's do almost exactly what I said. Error growth. So here's an example. I define a number, a partial sum of 1 over I. Okay, this is the type of stuff you do in calculus. So I define a number. If you need to start summing 1 over 1 plus 1 over 2, etc. Right, all the way up to n, and that's a number. And you want to compute this number. Now, as a model, that is kind of like what we did, but a little simplified. Suppose an error of epsilon is introduced by each division. And of course, you should say, how about the additions, right? I divide, I add. I divide, I add. There are divisions and addition. You can do that. It's just I only need division. So you have the perfect adding machine, but every time you divide, you're going to make an error. Okay? Then the computed, let's say the computed Sn, and you can define that to be Sn with a hat, right? You're going to get the wrong answer. You're just going to see how wrong it is. What is it? Well, you're going to be summing up a bunch of things, but every time you add, every time you divide, you're making an error of epsilon. Now this, of course, you might ask yourself, is this an upper bound or something? Well, it's a simplified model saying that you exactly introduce this error. That's never going to happen. The rounding that we talked about before is kind of random. It could be negative epsilon, it could be epsilon half. Just as a model, suppose you exactly add epsilon too much when you divide two numbers, right? Then this is what you compute. Well, it's pretty easy to see that you're getting the true answer plus you're getting the true answer Sn without a hat, and n times you're going to add up epsilons, right? So this is an example of linear growth, isn't it? Because if you look at the error, as we defined it, to be what you wanted minus what you got. So the error, and this is the absolute error, not that it matters. Let's call it En. What you wanted minus what you got is equal to n times epsilon. And this is what we call linear growth of an error. Okay? This error is introduced and propagated. It's not that bad. As I said, it can still be bad if you're doing 10 to the 15. But most likely, you'll be fine for most everyday calculations. Okay? So as an opposite example, or not opposite, but an exponential example, here's a so-called recursion equation that you might have seen. Did you guys take? They forced you to take Math 55, most of you, right? You've seen this stuff. Good. I don't have to motivate. When you solve these things, I'll just give you the solution then. So this is a so-called recursion, sometimes difference equations, closely related to differential equations that we'll be solving. In fact, when we solve numerically differential equations, we'll end up with discrete difference equations. So these things will come back and haunt us later. But anyway, so you've seen the techniques for solving this. For now, I'm just going to tell you the solution. The solution is Pn is equal to a constant, depending on the starting values, plus another constant. And apparently, there's an alternating sign. Okay, so you can find this solution. And you can plug it in and see that it's very easy to do. Let me just use this solution to show an example similar to before. And I'm going to set C1 to 1 and C2 to 0. And there's a good reason for that. So this could be a true equation you want to solve. It's modeling something real. And this is, sorry, that should be C2. This is sometimes called a pollution term. This is undesired. But mathematically, no worries, because it won't show up. C2 is equal to 0, OK? So everything is well behaved. And of course, Pn is equal to 1 over 2 to the n, right? This is true. This is math. No errors introduced. And this works fine. But now, of course, you go to the computer, and you set C1 equals 1. But as I said, every time you do something in the computer, it's not really exact. Bad example, because 0 is kind of exact. But you would start introducing errors as soon as you add. So let's just approximate that by saying that this 0 that you tried to get out of here ends up being epsilon. And you would think that 10 to the minus 16 is never a problem, right? Well, in this case, it's going to be a problem because it hits something that grows very quickly. So the error now, well, now the computed Pn is the same. If I use this hat notation again, it's going to be the true answer plus epsilon times basically minus 3 to the n, right? So in this case, the error was huge, depending on n, of course. But what's interesting is how fast it grows with n. So the error in en in this case is 3 to the n. Exponential growth. And we will see in chapter 5, one of the most, well, all chapters are important, but that's when we solve differential equations, that there are methods that sound perfectly good mathematically, but they don't work on the computer for this very reason. Okay? Yeah.
So, but in this case, that wouldn't happen because 0 is defined, right?
What would happen in the reality? I can, of course, make up an example that would trigger this, right? By making it bad if these numbers are a third or something that can't be represented.
If it was like a number close to 0, maybe that would happen.
Yeah, of course, it's close to 0. So you set this to 0 to begin with. What you'll end up doing, the reason, okay, so here's how to make it break. Exactly like I wrote it, it would work. And the reason is that you would have 1 there, and you divide by 2 to the n, right? And that, when you plug it in here, you would probably start with a 0 and 1. You would put a 1 here and a 0 there. You would multiply by 3, divide by. Since you're only dividing by 2, I think it would stay exact. My point is that if I put a 3 there instead, I make a similar example, but I just do something that isn't exact. Even if you start with an exact 0, you would introduce an error pretty soon, and that would have a similar effect. So I could say that if you're exact for a little while, but then at C5, you introduce an epsilon. If you at any point introduce epsilon, by all likelihood, it will be hit by this term. So in practice, you will almost not find anything. But I agree, just when things are 0, it might work out. These simple examples might be bad examples. But don't count on that. You always need to assume that the computers are making these epsilon errors all over the place. They define in the book stable algorithm. We want a stable algorithm that if you make a little epsilon error, it should not blow up. Unstable would be the second example here. Here's another term we'll be using a lot, rate of convergence for a sequence. Okay, you might have seen this before. Yeah.
Whether or not an algorithm is biased towards it, does it matter if we have to say whether it's stable or not? For example, if it's introducing small errors, but only in like one particular direction, so after a certain time the error would be huge, so would that be a stable or an unstable?
People would call the linear example stable and the exponential unstable. However, in the definition here, it's a very vague definition, okay? It's not, you see, I didn't even call it a definition, and they don't call it a definition in the book. It's a vague thing. Meaning, I gave the example of the supercomputer saying that this could be really bad, but it's still called a stable algorithm. You can, in fact, you can almost never do better than this. This almost always happens. So the definition is not clear. In reality, it's just you don't want things to blow up and destroy your answer. That's how you see it. All right, how about this? You have a sequence, a alpha, 1, 2, 3, etc., and it converges to a number alpha. Okay? And you want to ask yourself, how fast does it converge to alpha? Why do we want to do this? So what's going to happen, let me give you a perfect example that's going to be exactly what we do next week. Alpha is the true answer of, let's say, a root to an equation. You come up with a numerical method that tries to find that root. And you call those approximate numbers, it's actually an iterative procedure, so you start and you're wrong, but you're getting better and better. So you have alpha 1, alpha 2, alpha 3, and hopefully you can prove, or at least observe, that the sequence alpha I or alpha n approaches alpha. So you're getting to the right answer. Are you happy then? That's the question. So you're trying to compute an alpha, let's say 1, just because I don't have good examples. And I give you a method, and I tell you that it's all good. You got to do some computing work, and I'll give you a sequence of numbers that converges to the true answer alpha equals 1. Will you be happy? Exactly. So it's you wouldn't be too happy if, based on what I said, alpha of 1 million could be completely wrong. Right? It could be that you need to do billions of calculations before it's even reasonably close to the true answer. You need to quantify how fast it goes to 1. In calculus, we just throw in infinities and we're happy, right? But in practice, you want to know a little bit, right? Because in the computer, infinity is never going to happen. Infinity is going to be 1,000,000. You don't want to work too hard, right? So you need to know some numbers of this. And this is defined by simply saying, can we bound it by some sort of order? So let me give you two very simple examples. So here's one sequence. Alpha n, let's call it sequence 1, is equal to 3 plus 1 over n, OK? This is a sequence, and it would be very easy for you guys to show that it approaches 3, right? The limit as n goes to infinity is equal to 3. But here's another one. With the same result. OK? Which one would you prefer if it was that you had to do a fixed amount of work every time you take a step? I mean, the reason this is a bad example is that you will say just plug in n equals to 1 billion and you're done. So it's a bad example. But in the reality, as I said, you're going to do a lot of work and you get alpha 1. Then you do a lot of work and you get alpha 2. It's a recursive, it's an iteration, basically, right? So you don't want to go too far. Which one would you prefer? This one is better because it converges much faster. Let's say that you want, let's say now that we talked about accuracy, let's say you want an error of 10 to the minus 6. You would have to work 1,000,000 times here and only 1,000 times here, right? So this is better. And it's kind of obvious what I'm saying, but we'd like to quantify what it means. So we have this notation up here. If you look at the notation there, we call it, you find some other sequence beta n, and it's kind of up to you in this definition. You could make it anything, but usually we make it like an expression like 1 over n, like in this example here, right? And constants I don't care about, I just take them out. And that will put you an approximate number on how quickly it converges, right? And you've seen this big O notation before, have you? You say that the error here is actually equal to big O of some function. Well, it means exactly what it is according to this definition, namely that the function can be bounded by some other sequence, beta n, times some constant that you don't care about. OK? So in this example, we would say that this is equal to, so the limit, as I said, the limit of both of these guys, as n goes to infinity, is equal to 1, which is the alpha, right? And the same is true for alpha 2. So alpha, the true answer is alpha equals 1. But if you look at the first sequence, it's really going to approach it in such a way. 1, did I say 1? Well, you see, it's very easy to make. You shouldn't improvise on the blackboard. Now, it's equal to the true answer alpha, right? Plus 1 over n, clearly, right? Now, I just made this example because it fits exactly the definition. So by the definition, and the constant equal to 1, I can really say big O of 1 over n, OK? So this is what we call the rate of convergence. So I would ask you, OK, you have this sequence. And you would say, OK, the limit is 3. And I would ask, how fast does it converge? And you would tell me 1 over n. And it's really a little approximate, because there's a constant I don't care about. What if I replace that 10 by 1,000,000? What is then the rate of convergence? It's exactly the same. Or 2 over. You can change it. It's not defined. I could put 1,000,000 there if I want to, right? We don't care. We just care about. So what's understood in these notations is that constants don't matter. And they might matter a lot in practice. Suppose, in my example before, there's 1,000,000 there but not there. Will you now prefer number 1 over number 2? Depends on how far you want to go. Clearly, this kind of guy would be really bad initially. But if you want 100 digits of accuracy, this guy would win still, right? If you just want a few, you're probably better off with it. So constants do matter, but they are not in the notation. While this guy here is alpha plus order 1 over n squared. The way I wrote it here is stupid because I just gave a name. I just put an O around the actual error, right? So in reality, you can't. It's not that straightforward to just write it down. I mean, we could do various sequences. Let's go over to function. I kind of prefer. Yeah, let me do this example. to show that usually you don't have this expression as it is, and you have to. I want to show you the power of the order notation. So, so now my example is a sequence that is alpha n equals n cubed plus n minus 1 over 2n cubed. Okay? The limit as n goes to infinity, it's clear, you know from calculus, these n cubes will be dominating. It's 1. 1/2. I always get this wrong. Right? Now let's find the order here. So I would ask you, you would do this, and that's easy, and I will ask you, what is the rate of convergence? Well, it's not so easy now, right? Because it's not quite written like that. But it's almost as easy as there. You just have to do a little bit of work. So by the definition, you want to look at what you compute minus the limit. Absolute values, let's say, yeah, we can keep the absolute values for now. That's fine. So that's going to be n cubed minus 1 over 2n cubed minus 1/2. The absolute values are not that important. I think this is larger, but I didn't check. So then I can just take them away. And what is this? This is equal to n minus 1 over 2n cubed. Now what? Exactly, right? So we don't really like to. So the rate of convergence is not that well defined. I mean, you could say it's order of this, and you would be correct according to the definition. But as I say down here, normally you'd like something that is a little simpler, right? And since you're just going to get the rough order here, to begin with, the 2 we don't care about at all. That's a constant, right? But do we care about the 1? No. You got to bound it somehow, and just removing those would be fine. So it makes sense to do this approximation here, that this is always going to be less than, well, let's keep the 2 for now, but there's an n square. And it's really the square that tells you most of the thing here, right? And the 2 we take out as well. So this is really, by definition of the big O, it's equal to order 1 over n squared. That's how we write it. So that's, like the example over there, just showed a little bit how you hide constants and how you summarize things. Now, still, this gives you a lot of information. This tells you approximately how many n you need to get a certain error, modulo the fact that you don't know the constants. Moving on, we can do exactly the same thing for functions. These were sequences, right? Integer n goes to infinity, we have a sequence. What if you have a function where you have a little h that goes to 0, and you have this function f of h that approaches a value L? You can do exactly the same thing with the difference now that things are not going to infinity, but they're going to 0. Okay? So you look at this error here between what you're computing and the limit that you want, and if you can bound it by some function g for small h, we write big O of g of h. Same notation. And normally now, of course, we want something that also disappears, because after all, the error here, the g, is going to go to 0 as h goes to 0. So polynomial things like h to the p make sense. But there will be other examples as well. So this is best shown with an example. I think let's do a Taylor. I could come up with a stupid example first like this, which would be completely trivial. So let me go right at just showing how you do this with Taylor. So not necessarily Taylor, but what do I have here? We have e to the h minus 1 over h. So this is one of those typical sequences. This is what I want to call f of h. Okay? And you guys are supposed to know how to take the limits of these things. And you're supposed to know that this is 1. How do you do that? Well, L'Hopital's rule, I think you were trained to do, but then when you learn Taylor, you realize it's easier to just write out the Taylor expansion of e to the h, and it kind of works out. All right, so I'm going to ask, so it's all good. You know that this has a limit. And the analog here is that you don't want, you'd like to set h equal to 0, but on the computer, you pay a lot of effort for making h small. Okay? So the question is, how small does h have to be in order to be reasonable? Well, that's what this definition is trying to say. So by just writing it out, you can write this as, you look at subtracting this out. Maybe we'll just write it like this. We'll look at fh, and we expand the e to the h like this. Subtract out the 1, and we'll do over h, right? And it's clear that the 1s are killed here, and what comes out is a 1 that you already knew. And if this was just finding the limit, I would kind of just say the rest goes to 0, right? But rate of convergence means I'm interested in the next term, because I want to tell how bad that is. So the next term is basically going to be this guy. H half plus, and then it keeps on going, right? So what I said is that this is equal to the limit 1, which in the notation is called L. This 1 is equal to L, right? The limit. But then there's a term, and the half I don't care about. So the order of that term is h. Completely analogous to the previous thing. It's just that it's an h that goes to 0 instead of an n going to infinity. You don't know quite right now why I care about this, but I could make similar example. Just accept what I said before. You can't set h to 0 in a computer. In the calculus, you just let h go to 0 and everybody's happy. Here, setting h to 10 to the minus 6 is really expensive. And you're wondering, do I have to do it? Do I get away with 10 to the minus 3? I think you have some examples of this type in the homework. It's not even on this homework, right? No, it's not. Oh, I confused, yeah. So I'm talking about the following week's homework. Good. So this is, my rule is that I want to try to cover as much as possible on Tuesday that is due the next Tuesday. So this week's homework is going to be on the reviewable calculus and those floating point things. That's pretty straightforward. Any questions? Is this going too fast? A little too fast, maybe. You got to read ahead. And I was planning to do MATLAB demo, and I didn't. But there will be more times. So I'm having office hours now, as soon as I come back in my office. Thank you.